Okay, so today we're going to talk about integration by parts and a variation called recursive integration by parts. It's related to the last thing, which was repeated or iterated integration by parts. And it kind of works something like this. So imagine that you're doing the integral of something that requires integration by parts. So here's this thing that we're integrating. And then maybe we do integration by parts several times. And so there's some stuff on this side. Right, there's some things, and then somewhere down the line we have our original integral again with a constant out front like this. So recursive integration by parts does this thing where you do an integration by parts repeatedly until you get back down to a multiple of the original integral, and then you can add or subtract this back to this side however the sign dictates. I'm going to assume that, say, this is a minus right here, right? So we have dot 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 minus k, this thing. So I'm going to add k times the integral on both sides. So we can think about there being a 1 right here. And then when we have this, we have 1 plus k times the integral dx. And this is equal to these other things that we had. Now we're still trying to solve for the integral, so what we're going to do is we're actually going to divide by this guy here. So we can divide both sides by 1 plus k. And this is the basic idea of integration by parts. You define an integral, right? And you do integration by parts until you get a multiple of itself again. Add it back over, and then you have a scalar multiple of the integral as in terms of these terms right here. And then you divide by the multiple that's out front. So you'll eventually wind up at something like this. And we have these things here. We don't know what they are right now, but it doesn't really matter for the illustration purposes. And then you have the integral solved for in terms of the other things, and generally you're going to tack on your plus c right there. So let's just do an example of this technique. So the problem that I want to solve is the integral of e to the 2x cosine 3x dx. All right, so I'm going to choose my u and my dv like this. I'm going to make this u, and I'm going to make this dv. You could go the opposite way, but then you just need to keep picking it like that. So what we're going to do here is we're going to find our u, v, du, and dv. So our u is e to the 2x. Our dv is cosine 3x dx. When we integrate this, we do a u substitution here, and we're going to get a 1/3 from that. And then when we take the derivative here, we do a chain rule, so we're going to get a 2. And then this guy is going to be equal to u times v. So when I multiply u and v, I'm going to pull the 1/3 out front for simplicity. Have my e to the 2x from this term, and then my sine of 3x from this term. And this is going to be minus the integral of v du. So if I have the 1/3 and the 2, that's 2/3. I'm going to pull that out front. Then I'll have my e to the 2x, and then my sine 3x dx, like this. So if we look, this is not the same as this, so we're not done yet. So we're going to need to integrate this again, but this is an exponential times a trig again, so we need to do an integration by parts. So I'm going to pick my u and my v very similarly to what I did last time. U, I'm going to make e to the 2x. And dv, I'm going to make sine 3x. So that makes v equal to negative 1/3 cosine of 3x. Cosine of 3x. And here we get this negative 1/3 from integrating sine and doing a u substitution on the 3x from here to here. When we find our du, we do a chain rule, so we get a 2e to the 2x. And we can just copy down our stuff here. So we have our 1/3 e to the 2x sine 3x minus 2/3 times whatever this integration by parts winds up being. So this is uv. So I'm going to have negative 1/3 cosine 3x e to the 2x. I wrote that backwards than I normally do, but that's okay. Minus the integral of negative 2/3. So that's going to change this to a plus from the 2 and then negative 1/3. And then I'll have my e to the 2x cosine 3x dx. And then I'm going to need to simplify this guy. So I have 1/3 e to the 2x sine 3x. When I distribute this, I get plus 2/9 e to the 2x cosine 3x. So I just swap the order here for this multiplication. When I distribute this negative 2/3 to this 2/3, I get negative 4/9, the integral of e to the 2x cosine 3x dx. Okay, now if you look, this actually is the same as our original integral here. So I'm going to copy the original integral on the other side. E to the 2x cosine 3x dx. And I'm going to add this to both sides. So I have 1 plus 4/9, which is 13/9 when I add it. And then I'll have my integral here. And this is equal to 1/3 e to the 2x sine 3x plus 2/9 e to the 2x cosine 3x. So the integral is here. We have our multiple here, and it's equal to the things on this side. So we need to divide by 13/9 to get this side by itself, to get the integral by itself. What we're going to do, instead of dividing by 13/9, we're going to multiply by the reciprocal, like this, to make it a little easier to manage. So this reduces. So we just have the integral that we started with. Okay, so when we have the 9/13 distributed here, this 3 and this 9 will reduce like this. We'll wind up with a 3 on top and a 13 on the bottom. Plus, and here we'll have this 9 canceling with this 9, leaving the 2 on top and the 13 on the bottom. Like this. So 2/13 e to the 2x cosine 3x. And then we need to do our plus c because this was indefinite. So we have our final answer that the integral of e to the 2x cosine 3x dx is equal to 3/13 e to the 2x sine 3x plus 2/13 e to the 2x cosine 3x plus c. That's a little weird, but that's how this works. This recursive integration by parts just wraps back around through itself here, and then you just solve for the original integral from there. If we need to do some more examples of this, I can do this in another recording.